In fact, initially, I thought that I will tell something regarding the application of machine learning techniques in solving electronic structure in addition to DFT. But later on, Soman told me that we are celebrating 60th birthday of Sanjay. In fact, whom I consider to be my younger brother, I know since he was doing his PhD. As a matter of fact, when his PhD topic was being discussed in Satyamurthy's lab, so Satyamurthy called me because I was there for setting gate question paper. He told at night after dinner, so that no one can see you that you have come here for gate paper setting, we'll take you to our lab. And then we had a thorough discussion how he can, in principle, in fact, about fractal dynamics and other stuff, collisions from a fractal lattice. So, in fact, although I thought that Sanjay would have been around, I'm dedicating this talk. Basically, it's in quantum dynamics. So, to Sanjay. Now, here, in fact, we'll take a slightly different route, and maybe I will tell you something what this DFT community, there are maybe one or two people throughout the world, they are working on this. And this is something what we started in India. And as you can see that it's a quantum potential based approaches towards quantum dynamics. So I will have to tell you what is quantum potential, okay? So just to brush up whatever we have learned so far, like you know what is density, and single particle density is the basic variable. And then you know the Weinberg-Kohn theorems, all ground state properties of a system are unique functionals of the density. And for a given external potential, the energy functional assumes a minimum value for the true density. So you get the Euler-Lagrange equation, del E del rho as mu, where mu is Lagrange multiplier, is chemical potential. This, along with this constant, if you solve, you will get the density. So here you can see the number of particles and the potential through Schrodinger equation map to density, and the corresponding inverse map is DFT. So which tells that the map is invertible. Now there are problems when you talk about the Weinberg-Kohn theorems. Say people started extending the Weinberg-Kohn theorems, let's say to excited states, to time-dependent situations, and so on. And there was limited success. And here, like people like Theophilou, Walter Kohn also started, and then Hardy-Gross joined Kohn's group, and they have shown that you can, like they had given formal proofs that you can, in principle, extend the excited state DFT to lowest excited state of a given symmetry. I will tell you real life examples later. And ensemble of states in such a way that the excited state, considering all the excited states forming the ensemble, the total contribution should not exceed 50% of the 50% of the whole ensemble setup. Okay. Now, Madelung, you have heard in Swapn Ghosh's talk. So Madelung started exactly along the same time to explain the dynamical processes within a time-dependent framework. But as you can see that for one particular problem, you can analytically solve and get two fluid dynamical equations. So one equation of continuity and one equation of motion. So the actual quantum dynamics is mapped into the motion of a probability fluid of density rho RT and velocity VRT, or rho into V is the current density, under the influence of the external classical potential augmented by a quantum potential. So this is something extra. You can see that you are mapping the actual problem to the problem of the fluid dynamical motion where you don't have a real fluid, the fluid is the probability itself, and that tells you how the probability is changing from one point to the other and also from one time step to another. But here you can see that the probability of fluid is acted on not only by the classical Coulomb potential what was there before. In addition, you have something called a quantum potential which is originating basically from kinetic energy. So, you are generating a potential energy from kinetic energy, and that we will see how it comes. So, this is something what you can do it yourself. This is a very simple algebra. Say you start with, I am starting with one particle problem. H psi is I h cross del psi del t. I is of course square root minus 1. Now, for single particle of mass m, I can write the Hamiltonian like this. And then what I do, I substitute a polar form of the wave function r e raised to I s by h cross, where r and s are two say scalar quantities, and r is related to the density as rho to the power half, and s gradient of that by m gives you a velocity, whereas the current density can be given as the rho times b. So, if you know the wave function and write it in the polar form, immediately you get the density and the current density. So, now here if you put these two in one and separate out the real part and the imaginary part, then you can immediately show that you will end up into two equations from real part and the imaginary part. One is del rho del t plus divergence of j is 0, that is the equation of continuity, and equation of motion is del v del t plus v dot grad v. That means you can write it as total derivative d dt if you add these two, minus 1 by m gradient of v plus v quantum, where v quantum is the quantum potential is coming as minus h cross square by 2m del square r by r. So, here you can see it is like basically kinetic energy. R is rho to the power half. So, minus h cross square by 2m Laplacian, only this is the way you define the quantum potential. And my talk would be basically based on several quantum potential based approaches. Now, if you solve these two equations, obviously you can get density and the current density. And if you get the density and the current density, starting with some initial wave function at t equal to 0, you just simply solve iteratively those two coupled equations. You will get at every time step how it is evolving in course of time, the density and the current density. Now, the thing is, it was assumed, let me tell you, later on we know it took actually 1964 to 1984, exactly 2 decades for Runge and Gross to come, and so no, in principle you can write in a time independent situation, as you have seen that Hohenberg-Kohn had shown that any physical or chemical property you can write as a functional of the density, but what it was only time independent situation. But if you go to a time dependent situation now, so Madeline is claiming, I am telling claiming in the sense because it was not proved at that time. It was the same year when Schrodinger is giving his own equation. So, it is telling that now in principle, if you know the density and the current density, in principle you can write any dynamical property as functional of density and current density. Remember, at that stage itself he could identify that density alone cannot tell you about the time dependent problem solutions. You have to bring in current density. Okay. Later on we will see, whenever you will bring in current density, excited states also will come into the picture. Okay. Because suppose you start at time say dependent problem at t equal to 0, you have some kind of wave function, and under some external field, let us say it is evolving time dependent external field. Once you switch on that process, time evolution process, you might have started from the ground state of the system, but with the zero current density, let's say, to start with. Immediately after, you will see the current density is, say it is, it started accumulating. Whenever you are getting non-zero current, that means you know the excited states are now getting amalgamated into your ground state. So, in a sense, the time dependent part and the excited state part, they are intimately linked. You cannot avoid one from the other. So, we will see. So, they are connected. But you can see the Madelung problem was, in fact, only for a single particle case. If you do it for many particle case, you get quantum fluid. So, this is the whole subject is called quantum fluid dynamics. Okay. So, this is a form of time dependent density functional theory. Now, this quantum fluid dynamics, if you do it for many particle case, you get the quantum fluid dynamics, but that will be in 3n dimensional configuration space. So, you have done so much of work in order to reduce the dimensionality of the problem from 3n dimensional to 3 dimensional. So, although you are getting a physical picture of a probability fluid, but it is in a 3n dimensional. So, you have lost that elegance what you are after. So, you want to bring down the quantum fluid dynamics to 3 dimensional space. Okay. So, there have been attempts. So, there are papers like you go to the orbital picture, this standard approach time dependent Hartree-Fock, time dependent quantum, expand in natural orbitals, so that you get some n component fluid and you get a quantum fluid dynamics in 3D space. So, we are going towards quantum fluid dynamics in 3D space. That means we have to have a single component electron fluid. Okay. Then in 1984, again, these are existence theorems. So, Runge and Gross, they had shown that actually you can write Madelung-like equations like this, equation of continuity and some equation of motion. And here you can see that what, in fact, if you see the gist of Runge Gross, you can get, of course, many offshoots like time dependent quantum in orbital picture that I told immediately, so that you bring back some 3 dimensional stuff or time dependent, say Hartree-Fock or even natural orbital will bring back some kind of stuff. But here, if you want to be there in the same, with the same flavor of Madelung stuff, so you get, it is there in Runge-Gross proof itself, that you get the equation of continuity, but equation of motion you get del J del T is a functional of rho RT and GRT. So, but you have to prove this. So, Runge and Gross had proven this. Okay. But it was analytically derived by Madelung for single particle. So, you have to construct this approximate functional. So, that is your goal. Like in Weinberg-Kohn theorem, they are giving the existence theorem, but somehow you have to construct that functional. Here also you will have to construct the functional. Long ago, so when I was doing my PhD, we did this. I am going back, you see, to so many years. Maybe none of you were born by that time. So, in those days, so what we have shown that, as Sapan Ghosh was telling, it is the kind of marriage between QFD and TDDFT. So, we developed something called a quantum fluid density functional theory. Okay. So, that means we have made use of TDDFT within a quantum fluid dynamical framework, and this derivation actually takes time, but it is not at all difficult. You can do it very easily. So, in this paper, in the appendix, you can see maybe 4 or 5 pages derivation is there. Okay, so that you can check. Yes.
So when you assume that velocity is derived as a gradient, aren't you making the same approximation that Bloch did in time-dependent Thomas Fermi, that velocity is a
you see the original one came first by Poincare, then by Bloch. In fact, it was gradual development. But if you see the algebra, clean algebra for single particle was by Madelung. But if you want to get some kind of say confidence through proper proof, that is Rangai's proof.
No, that I have no problem.
And
In your equation, when you say that the velocity is a gradient of something, aren't we already assuming that is vortex free?
that is another thing. This irrotational stuff you can. So this gauge invariance, etc. Ghosh and Dhara, they did it. Okay.
But here that assumption is there.
Yes, yes.
Because I also derived from time dependent differential equations here. There one has to make that assumption.
Right. You're right. But Ghosh and Dhara, they have shown. Yeah, but they have shown it. So now you see that you can get this. This is your velocity potential. That means if you take the gradient, it will give you the velocity. So now you are getting the time evolution of the velocity potential. Here you can see you are getting something like a kinetic energy. Then you have del G, del rho. Well, this is your typical Hohenberg-Kohn type functional. This is your Hartree type potential, and this is the external potential. Okay, and this is the velocity potential. So here, what you can do, you are now having these two equations. What we did, so first we derived these two equations, and then again we went back in the direction, in the reverse direction, to check whether we can get a single particle like equation, which is kind of time dependent Kohn-Sum like equation. But the thing is, here you can see that this phi is a single particle orbital like quantity, and this is the effective potential. Here you can see, and this equation is generalized nonlinear Schrodinger equation. Many people now, they have started calling it DC equation, Chattaraj equation. So this equation is solved by many people for getting dynamical characteristics over there. So in this case, you can see these are various functional derivatives. So this is the non-Weizsäcker part, and then you have exchange correlation, and this is Hartree type classical Coulomb, and this is the external potential. This phi is related to rho to r to the power half e to the power I is I. So this is your velocity potential. Okay, and time dependence is coming here, and rho RT is phi RT mod square, and J RT phi real grad phi imaginary minus phi imaginary grad phi real, which is same as rho. So that means density and the velocity product is the current density. That's the standard definition what we are getting. Which one? You see, it is like this. Say, this is a kind of orbital free DFT where the kinetic energy functional is written as the density functional. This is the standard way. So, Manoj has told elaborately, but maybe he will tell something on the inhomogeneity correction through Thomas Fermi theory. So, there, inhomogeneity correction is, it was given by Weizsäcker, because Thomas Fermi is the homogeneous electron gas. So, Weizsäcker had given that say 1/8 integral grad rho dot grad rho by rho dr. That was the inhomogeneity correction what you have to add. Later on, you can see for getting your kinetic energy functional in the sense not going to the orbital based picture in Kohn-Sum, you write in the form of density itself. So obviously you can get kind of gradient expansion, and the first one is called T0 is your Thomas Fermi term. Then 1/9 of Weizsäcker is the T2. Then you have T4, T6, etc. You can get similarly for exchange also you will get Dirac exchange plus then K0, K2, K4, etc. Okay. So that whatever is there other than the Weizsäcker, if you dump into this in the kinetic energy functional, that is non-Weizsäcker part of the kinetic energy functional. Okay. I saw there are 2 talks on kinetic energy functionals. Incidentally, we have developed our own functionals. We have our own functionals. There are 5 or 6 physical review papers, derivation of kinetic energy functionals. Again, unfortunately, Ehrenberg didn't say, but fortunately for us, so that we could. And they give good numbers when you substitute, let's say, sometimes the Hartree-Fock density into this to get kinetic energy. And if you put it there in the Euler-Lagrange equation and the density what you get, then if you put that density for calculating properties, so that's a further difficult check. So that also we did. Okay. So now, what is the, say, machinery now? Let me think about this. Say, it is, you start with some wave function to start with in a given dynamical problem, and then you know the external potential. This external potential here now will contain some real external potential, like you think about a collision or you think about atom field interaction. That is also included in addition to your say electronuclear attraction potential. Okay. So this is standard time dependent external potential. So you know that potential, the physical problem at your hand or the chemical problem at your hand, and then you solve this problem. There's a time evolution of your density and the current density. So at the very beginning you get density, current density, or maybe the corresponding velocity potential, etc. You get the time evolution. In the next time step, if we know the actual time dependent functional form of any given property, as I told you, Runge-Krauss has told that it will be functional of density and current density. Now at every time step, I am getting for that dynamical problem density and the current density, and I plug it in those properties, including I will talk about chemical reactivity. So this is the reactivity dynamics when a chemical reaction takes place, how the reactivity parameters are changing in course of time. When one, let's say the hardness of this, another say reactant is approaching, how its hardness is changing. So this is a time dependent problem, and that is at the heart of the reactivity. You cannot tell only static reactivity parameters. So the first thing, if you know these the functional of density and current density, etc., and you solve this equation to get density and current density at different time steps, then you can in principle follow the time evolution of all those properties. Okay. So you can see that now we are in the process of developing a dynamical strategy to follow a dynamical process within a density functional framework. Okay. Now here I am taking a detour because I will bring many different, because 1.5 hours, isn't it? So many different stuff. So you will learn maybe several new things which you have never heard of even. Okay, but they were all done before you were born. So you have to learn something. Now I'll just read this one because this is important. If I get time, I will tell something very interesting. Say, although classical mechanics is deterministic, it was taken from quantum chemistry by Ira Levin. It was realized in the 1970s that many classical mechanical systems, for example, a pendulum oscillating under the influence of gravity, friction, and a periodically varying driving force, show chaotic behavior for certain ranges of the system's parameters. In a chaotic system, the motion is extraordinarily sensitive to the initial values of the particles' positions and the velocities, and to the forces acting, and two initial states that differ by an experimentally undetectable amount will eventually lead to very different future behavior of the system. For example, a physicist constructed a double pendulum for which the gravitational attraction of a raindrop 1 mile away is sufficient to greatly change motion after 2 minutes of oscillations. Okay. Thus, because the accuracy with which one can measure the initial state is limited, prediction of the long-term behavior of a chaotic classical mechanical system is in practice impossible, even though the system obeys deterministic equations. Computer calculations indicate that the motion of the planet Pluto, anyway Pluto is no longer a planet, may be chaotic. Now, what exactly is this subject? You can see that we are entering into a totally different subject. This is classical chaos. We'll bring something, what is quantum chaos in a quantum system. So what is this? The sensitive dependence to the initial conditions. And for a classical system, although the classical equation of motion like Newton's equation of motion or Lagrange equation of motion or Hamilton's equation of motion, they are all deterministic equations. That means they have a causality. If you know at t equal to 0, you know what would be at delta t. But the thing is, these are initial value problems. So you have to supply the initial conditions in order to solve those dynamical problems. Initial conditions, even if they differ by sometimes 10 to the power minus 12, you can see exponential divergence of the trajectories. So as it is written, suppose if you want to get the initial conditions even from some experiment, you cannot detect that much error, and ultimately you don't know what will you get. And say you start from the same initial condition, you will get different behavior also. And this is why I am telling, say whether you do single precision calculation in computer or double precision calculation, still some gap is there. And that gap is sufficient to cause exponential divergence. Now for a quantum system, we will take mostly quantum domain behavior of a classically chaotic system. Say classically chaotic system, let's say governed by classical Hamiltonian. What we will be doing, we will be simply changing the classical Hamiltonian to the Hamiltonian operator of the system, and with the same set of parameters where it is showing regular behavior or it is showing chaotic behavior, we want to see the corresponding Hamiltonian operator. If I know, I can solve in principle the Schrodinger equation and get the time evolution of the wave function and other properties, whether the corresponding properties, whether we see what is the signature there. Okay. So that I will tell towards the end. This is something, say, HSAB principle applied to the time evolution of chemical reactions. I will have to tell a little bit over here. So this is your electronegativity. Hardness, perhaps you are seeing something new, but this can be derived from DFT, remember. And say hardness is written as this double integral, and this is called hardness kernel. You can say hardness kernel is the basically like you only told and Vamsi about kernels. So you can see, remember I am not writing any row within bracket. Kernel is not a functional in true sense. So you are taking second derivative, del rho r prime. This is your hardness kernel, which puts over here. And Manoj, if I am not wrong, changing rho r to fr, that is your job or someone else? So this is when we are doing this local hardness.
That this eta rr prime to fr prime dr prime itself is a constant. 1 over n rho r integration is redundant.
Yeah, no, but in a time dependent situation, no, I'm telling. No, so and there is a polarizability, etc. So here at this stage, let me tell you something. Say because Soropal was in a hurry after his second talk, so I could not tell something which I should tell you people, you must know. So the first thing, these reactivity descriptors, they are best described in terms of the associated electronic structure principles. So first I will tell you two of them. One is the maximum hardness principle. Another is the hard soft acid base principle. In fact, when I was, Manoj was also there that time in Professor Par's group in 1990, we had provided some formal proofs. The first one from the applying fluctuation dissipation theorem of statistical mechanics, and the second one through the energy optimization when there is electron flow from say base to the acid in hard soft acid base stuff. So point number one, say that paper incidentally Soropal had shown RG Par and co-workers, and co-workers is Pratim Chattaraj only. So he somehow didn't want to take my name and wrote it in, say, Gaurav co-workers. So this is something. So that was our paper. And what he showed about those water vibrational modes, in fact, exactly that work was done 3 years before by Pearson and Palke. Only job what he did, Pearson Palke calculated I and A using DFT-based method. He did it using couple cluster. So that is the contribution. But actual problem, solution, conclusion, everything was done by Pearson Palke. Now, the second thing, he talked about local HSAV principle. That I'm going to tell it for the sake of completeness and for the to put the record straight. It was originally, he also took the name Gasquez and Mendez. They had shown the local HSAV and applied, published a couple of JAX papers there, and maybe from there, Soropal and others, they got the inspiration and did some calculation. So when you go to the local level, and what I am telling, these are the extended stuff. If I cannot finish it 1.5 hours, maybe you have to give me some more time. So the extended this consideration, in fact, local HSAV requires the definition of atom in a molecule. So you have to define first, partition the density among various atomic basins, and you have to define the atomic basins like Mulliken, Loveday, Herzfeld, Bader. You can have your own definition of atoms. So this is, although the chemists love to talk about the atoms in the molecules, but quantum mechanically, once molecule is formed, there is no existence of the atoms. Okay, but we have to do something. We have to talk about population. We have to talk about this, that, etc. Calculation of Foucault function and this. So condensed to atom variants, if you want to do. Now, the problem was known. Second thing is, if you talk about the hard soft acid base principle within the atomic site, what is their problem? So I thought that it is not possible. So because I told you that we published a paper, say back-to-back two JAX, one with the HSAV principle, where we had shown that you can minimize the energy within the whole molecule. Whether it is possible to get that type of energy minimization within an atomic basin, which is the crux in the application of the local HSAV. So I had done all calculations and I had shown that it is just not possible. Then in order to get some confidence, I consider Richard Bader is the person who had given the most like physically meaningful definition through zero flux surfaces of the atoms in the molecule. And So in that sense, Bedard church or Bedard's population is physically the most meaningful, not the Mulliken or Lovedine or Hersfeld. Although he used Hersfeld, but I consider, let's say, the better one. So I had a long 2 hours discussion with Richard Bedard that this is the claim, many people are publishing papers, and because it is talking about DNA, these, that, it is getting published in JACS and all sorts of PNAs. So what do you think? Can we just really get a local HSV principle? So, but I had shown my derivations that it falls flat. You cannot actually just minimize this interim stuff. They have absolutely no meaning. The population has absolutely no meaning. Only thing you have that you sum over all QK, that will be the total number of electrons. Nothing else. You cannot do anything. So if I tell that, in fact, some population analysis scheme is showing that lithium hydride, say lithium is negatively charged, hydrogen is positively charged. Mulliken is most dangerous. You will see always this is coming, and that is because your density partitioning has no physical basis. It is arbitrary. So I did, without considering any specific population analysis scheme, I've shown that you cannot have any energy minimization within the atomization. And Bedard gave me the confidence. I wrote one single authorship paper in JPC, I think in 2000 or something. And then even Vasquez Mendez and others, they have stopped talking about local HSV principle, except a few people. They're still showing because it was published in JACS. But I am telling you, you take local HSV principle with a pinch of salt, which I wanted to tell that time itself, but he left. We got some phone call from airport and so on. Now, in this case, other principles, why I am telling about the principles, because in a dynamical situation, we'll see their effects. So we have shown, we have provided in a dynamical framework a proof of minimum polarizability principle, that a system evolves towards a state of minimum polarizability, and that is shown by many, many people afterwards. And about the electrophilicity, which is mu square by 2 eta or chi square by 2 eta, electrophilicity, in fact, a stable system or a spontaneous process also is associated with the minimum value of the electrophilicity. Actually, we had given the proof, formal proof of minimum electrophilicity principle also. So first proof was a general proof during a chemical reaction on, say, along a reaction path that we derived with my old friend. Unfortunately, he expired just 2 months back. He's from Santiago, Chile, Patricia Fuentelva. We were there together in first group. So Patricia Fuentelva and myself, we published a paper giving a proof of minimum electrophilicity principle. And later on, we extended it to vibration, rotation, chemical reaction, etc. And we published another paper, that is myself and Subbu, your V. Subramanian here. So these are the electronic structure principles which can govern or rationalize any given physicochemical process like vibration, rotation, and different types of chemical reactions. And there are thousands and thousands of papers. You can see like that Arjipar and co-workers, that paper has more than 1,000 citations. And similarly, HSAV also has. Because that was applied by many, many people in many different occasions. Okay. So, more or less, I'm not telling their proofs are not having any counterexample, etc. But as such, some acceptable proof, formal proof, like application of fluctuation dissipation theorem or energy minimization. So you can get them. We will see why I'm telling so much, because we'll make use of those stuff. So you remember, so these are the definitions over here. Okay. So now I will show you some results. So this is what we are calling reactivity dynamics. Reactivity dynamics means I write them in a time dependent framework. What are the corresponding forms? Is the time dependent density and current density type functionals. And here we are considering excited states also, remember. But deliberately we have chosen only those excited states like which are lowest state of a given symmetry, and also in an ensemble we have chosen in such a way that the excited state contribution doesn't go beyond 50%. So once we did this, first I will tell you the time evolution of the chemical potential. So let me reiterate. So what we did, we just say we are solving the so-called generalized nonlinear Schrodinger equation, and with the wave function, what we are getting here, these are say, and the wave function quality is very, very good. So time evolution of chemical potential, so for various species like helium isoelectronic sequence, helium, lithium plus, beryllium 2 plus, boron, beryllium, carbon, and so on. Okay, beryllium 2 plus, boron 3 plus, carbon 4 plus. Then what we could see that as, so this stuff is colliding with a proton. Okay, so proton is coming and it is sitting over here and it is experiencing the incoming proton and the corresponding change. So we can easily calculate the Coulomb potential between this and that and add it to your external potential. Okay, and then you solve the equation as which one? In some sense. So now you can see that what we could see that when the proton comes, say gradually the chemical potential behaves like this, there is sudden drop, and then you can see that it cannot be calculated, chemical potential. After some time again you can see that it can be calculated. So it says that you can differentiate the whole collision regime into 3 different fragments: approach, encounter, and departure. Whatever chemical reaction or if it is to happen, it is there in the encounter regime, and the chemical potential tells you, you see this is as a function of time. So at what time you will get, and you have some initial velocity, impact parameter of collision, etc. of the proton relative to some, let's say, static position of the target. This is the projectile. So here we have taken various electronic states, 1s, 1p, 1d, 1f. So you can see, so for a given symmetry, I am taking the lowest excited state, not same symmetry. Like I am not taking 2s and 1s together. Now in this case, if I check now, you can see the hardness is getting maximized in the collision region. So that is basically nothing but the time dynamical variant of the maximum hardness principle. What it says that when it is encountering, there is kind of so-called chemical reaction in a dynamical framework, the hardness maximizes. That gives you a signature that something is happening. at that time. Otherwise, you can see it was almost zero. Zero in the sense relative to this. Obviously, it is not zero. And not only that, you can see the various excited states, how they are changing. Hardness is decreasing for different excited states. So, I am showing two different aspects here. You can see one in a dynamical framework, when some favorable reaction is there, suddenly there is a spike in the time dependent hardness profile. Hardness was defined with the hardness kernel, and the hardness kernel was defined as the second functional derivative with respect to Weinberg-Kohn universal functional, and Weinberg-Kohn universal functional as the density, and in fact current density also appears after a certain time. And then if you take the functional derivative, you can write it in a form, and you are getting density, current density, you plug it there, you get hardness kernel.
Is happening, the hardness is satisfied. How can I think of from that static picture?
No, you cannot extend. So dynamics, with say there you didn't have any current density and other stuff. It is coming now in excited states. Now you can see. So this is time dependent variant, and what you could show that in fact we had shown also in one of the papers the HSAB principle will obey where maximum hardness principle is also obeyed. That means it's a kind of precursor or necessary condition for HSAB principle to be obeyed. It must obey the maximum hardness principle. Now here what is happening in a dynamical framework, not only you are having maximum hardness principle, you have HSAB principle also. Okay, and that is something what we publish some papers to show the excited state reactivity. What is that excited state reactivity? That your ground state is the most stable. If you keep on exciting a system, it is getting more and more unstable. Okay. So if you follow the simple minimum electrophilicity principle, minimum polarizability principle, and maximum hardness principle, you would expect that if you keep on exciting your system, your hardness will decrease, polarizability will increase, electrophilicity will increase. We have shown in a number of systems, atoms, molecules, we got the exact whatever available excited electronic state wave functions, it is obeyed. Okay, so you can see, although it looks very much qualitative, but its signature is there everywhere. So they are obeyed. Now we twisted this problem now a little bit. What is that? Say, first, if you just electronically excite your system, let's say helium or lithium plus or beryllium 2 plus, these are all helium isoelectronic. We have taken isoelectronics equations, sequence so that you can compare them. Now, in this case, what is happening that when you have the electronic excitation, gradually hardness is decreasing. Proton is a hard acid. Okay. So proton would prefer to interact, let's say helium atom, in its ground state, where it is the hardest, according to hard soft acid base principle. And that propensity will decrease as you keep on exciting the helium atom. That means it's HSAB principle in a dynamical framework. So first I have told you about the MHP because of the maximization of hardness and minimization of electrophilicity, that is now you are getting something else. That if you keep on exciting the, say, height, ground state has the maximum height, then if you keep on exciting, the height is decreasing. That where you have the maximum, the value of the maximum, or in a sense, the ground state will give you maxima of maximums, like the supremum value. Similarly, the infimum value will come for the electrophilicity. So this tells you that in a dynamical framework, you can get the maximum hardness as well as minimum electrophilicity principle, the manifestation of those principles within a dynamical framework involving excited states. Okay. At the background, what we are doing, we are solving that Q of DFT equation, what we derived. We did the same thing for the two-state ensemble. And as I told you, two-state, we have taken it, and here we have considered the previous stage and also helium, neon, argon, krypton, xenon, and we could show exactly whatever is expected is coming very well, even for the two-state ensemble. Okay, so in a two-state ensemble, you start from only ground state, then you put little bit of excited state, then so that of course the total is normalized, and then you keep on increasing the excited contribution so that it doesn't cross the 50%. So you get various types of ensembles. You calculate for all of them, and you can see the same thing is happening. If you have more amount of excited state, it is the hardness is decreasing more. Okay. Then we wanted to study a chemical reaction like molecule plus proton, and here you can see the hardness and the electrophilicity. If it is coming from this side or this side, because this is symmetric, you get it like this, the dynamic reactivity profiles of chemical reaction. Okay. So this is it tells you some details about the chemical reaction. Which one? Atomic unit. Yes, because there is a singularity there. Coulomb singularity is coming almost. Now we did something else. We considered first H2, it was symmetric, but now you can see I can talk about the regioselectivity of the chemical reaction in a dynamical framework. If you have, say, collision between carbon monoxide and proton, you can get either formyl or isoformyl cation, and then comparing the heights here or depths over here, I can tell, at least in a dynamical situation, which say there are two possible products, formyl cation and isoformyl cation, which one would be more favorable? And we can see the corresponding weightage in the product ratio. In it, at least when the dynamics, when the reaction is going on, later on your thermodynamics, etc. will take, but now when the dynamics is going on, we can immediately tell, comparing the heights of the hardness profile and depths of the electrophilicity profile. Okay. Now we did something on the chaotic ionization of highly excited helium atoms in the Rydberg state. So these are the known formula from some publication we had taken, and we had shown this. So I don't want to bother you with this. So what we have shown, I will tell you only the result, that we are starting another dynamical problem. Say we have shown, of course, the chaotic ionization also, and this is simple hydrogen atom subject to some external electric field. as you can see, the hardness decreases in the ground state, and the excited state, the decrease is not that much. So, what we could see that oscillation part, that I will bring in this in more detail. So, maybe I will bring in those stuff in somewhat detail at a later stage. So, here you can see we are having in quantum fluid dynamics probability, current density, equation of continuity, equation of motion, velocity potential, universal one-word cone functional. And this is generalized nonlinear Schrodinger equation, this. And these are the standard functionals like exchange correlation. We have taken Dirac exchange. Dirac exchange is that minus Cx integral rho to the power 4/3 dr. What do we call LD? Huh? So you call Slater, but it was originally derived by Dirac. That's why I wrote Dirac exchange. And some Wigner type correlation energy functionals. Okay, we have taken Ciperli order and others also. So in external potential, you have minus 2 by r plus epsilon sine omega t. This I call field problem, and this is minus 2 by r1 t minus r prime minus 1 by r2 t minus r. So this is the collision problem. So we are adding this in addition to whatever we had before. Quantities calculated: hardness, chemical potential, electrophilicity, polarizability, and we have, in fact, we derived this entropy for say the density distribution. You can define this entropy. So this is basically coming from what is called a Sackur-Tetrode equation, and yes, and this entropy, as you can see, that it's basically it's integrated over r. That's why it is just a function of time. Numerical techniques, what we have done. So in both the cases, actually we have cylindrical symmetry of the problem. So we went to the cylindrical polar coordinate systems, and we transform the coordinates. So the GNLSA takes this form. We have the initial condition that this y is known for all x and z at t0, y0 z, y infinity z equal to 0. Boundary condition is this, and we are considering two stuff. One is the effect of the time dependent external field, say collision or electric field interaction. We have shown the magnetic field also later, and we are incorporating a confinement. Confinement means we are considering that we are somehow you are using what is called a Dirichlet type condition. We are cutting off the density to 0 forcefully, and the whole electron density is forced to be there within some radius or some volume of the cylinder. So schematic representation for the atom field interaction. So you have the helium atom, apply the field, let's say you are like this, and you are confining it, then you get this. And helium, you have excitation, apply a field, and then confinement. Another one, helium interacting with proton, you get HH plus, confined, you get HH plus, excite this helium, do exactly the same thing. So these are the processes what we are going to study in a dynamical framework. What are you doing here? This one. You see the transformation, why it is done, let me tell you. Say, if you see the wave function for an atom, it varies very rapidly near the nucleus relatively very, very slowly away from the nucleus. Let's say it goes something like this. Now suppose if you are talking about, I am going straight away to your numerical part. You are discretizing the mass. Okay. If I tell, let's say along rho tilde direction or along z direction, I have the mass. Okay. If it is a simple atom, I have as a function of r. Understand? If you have a linear mass, straight cut in r itself, then what will happen? You are giving same number of mass points where it is very rapidly decaying and where you don't require anything. There also you are doing the calculation with same number of mass points. Now think about this. I change the variable not as a function of r equal to x square, very simple. If I give x square means what? When it's less than 1, how will it behave? Tell me. Now I am transforming my whole equation to x, where r equal to x square. That means the same mass when I apply in x square, it is giving more number of mass points near the nucleus, much less number of away from the nucleus. I can do it with exponential mass, even better. Okay, it is behaving exponentially, my mass is also exponential. Like I transform my r variable to x variable, where r is e to the power x. Okay, so wherever r is there, I can immediately convert it to x, and my mass points will be very closely spaced near the nucleus where it is rapidly varying and very widely spaced. Do you understand? Okay, so you have learned technique. Of course, I don't know whether these days people write program or not. We wrote our own program. Remember, this is at least 15, 17,000 statement program what we wrote ourselves. So you had stability, convergence, consistency, all those problems we had to tackle. Okay. You have seen Utpal's paper also, I have shown. That's my student Utpal is now in the physics department, Central University, Assam, and she is her student. So, anyway, so this is something what you have to learn, that black line is unconfined system, red line is confined system, blue line is confined system, and these are the lengths of the cylinder. For excited state, you have to do some other set. So, atom electric field interaction. Now, these are basically results. I will go very quickly so that at least I assure you that I will tell you something related to quantum chaos. So, I must keep some time for that. So, what you can see that if you have the time evolution of chemical potential of ground and excited state helium placed in intense laser field, so what you can see that chemical potential oscillates in phase with the external field. That is as expected. It's a first order variation. Second order, you see these are various field strengths. It's almost not changing hardness, but hardness oscillations, if you want to check, you have to wait for a very strong field. Why? Because hardness is a second order response. Chemical potential is the first order response. Then you get similarly electrophilicity, polarizability, entropy. Now I am talking about a collision problem, proton and atom. So this is something what we have already seen, collision problem, what is happening. But in addition to this, now I am talking about, say, confinement. Okay, that means now you have the effect of collision, you have the effect of confinement, you have the effect of excitation. So first one at a time, then two at a time, all possible variations, then three at a time. Okay, so one is the effect of collision, one is the electronic excitation, another is confinement. Okay. So we did for proton and molecule, and here the kinetic energy functional for the proton molecule collision is like this. So here again, these are the pictures what we could get. Proton and H2 molecule, molecule electric field interaction, atom magnetic field interaction. Here also you could show how there is a time evolution. Now, one important thing what we could see, that you have electronic excitation in a given time dependent problem. Let us say electronic excitation, you have confinement. We have shown in almost all cases that if you can properly tune these two, say, parallel processes, you can bring back the ground state behavior. So you are electronically exciting a molecule and then you are doing confinement, it will behave like as if in its ground state. And that we have shown in a number of cases.
What behavior tells you?
I am doing the same thing for the ground state. I am superimposing that on the ground state. Exactly same. Okay, how much confinement, how much, that you have to tackle depending on the problem. But you can just simply do one above the other. Okay. Which electronic excitation, how much confinement, that you can tackle. In most cases, you can do this. Okay. Now, I am switching the gear. Is quantum Helmholtz oscillator. So first I will talk about the classical Helmholtz oscillator, and there is something say interesting physics what we could derive. Say this is the Hamiltonian where the potential is given by this, and time dependent Schrodinger equation. Now what I am doing? The classical Helmholtz system, it is known to exhibit classical chaos depending on the values of the parameters. For some parameters, it may show say exact regular behavior, and for some other parameters, it will show chaotic behavior. Chaotic behavior, I will tell you certain say diagnostics to understand the chaotic behavior, standard diagnostics. Now we wanted to check what we can do say for the corresponding quantum version. So very simple what we did. So this is your classical Hamiltonian for the Helmholtz system. I just simply write this and then time dependent Schrodinger equation, get these two QFD equations. Now what we have shown here, that these two QFD equations can be also be obtained as following Hamilton's equation of motion. And remember, this we had shown it for the first time. Now many physicists are applying this. So what is this? That if I write del H del rho, it is del chi 1 del T, and del H del chi 1 is minus del rho del T. So this is something what you should see, and chi is just simply minus xi, xi is the velocity potential. So what I am doing within a quantum fluid dynamical framework, I am deriving this as the classical Hamilton's equation of motion, where rho and minus chi, now or rho and chi in fact, they are becoming canonically conjugate. Canonically, no. This I am telling, I will tell you the difference between blocks and this one. So here what is happening, you get a macroscopic kinetic energy, Weizsäcker term, and let us say some potential. So like x and px are canonically conjugate, so you get the phase-space trajectory reveals the classical chaos. Now our starting point is, because we can derive our quantum fluid dynamical equations, that's basically the quantum description, from considering rho and chi, like density and the, let's say, velocity potential, as the canonically conjugate variables. And in classical chaos analysis, we consider momentum and position as canonically conjugate variables, and there you plot them to identify whether it is motion is regular or chaotic. Can we do the same thing using rho and chi now for the quantum system? Okay, so you can see this kind of adventure, getting some cue from this that they behave like canonically conjugate. And we have derived also that you can do it from least action principle also exactly in the same form, considering rho and xi is minus chi. So you can do the least action principle. Exactly, you can go back to that. So again, we have the initial boundary value problem solved numerically using alternating direction implicit finite difference scheme with Dirichlet boundary condition for R and Neumann boundary condition for chi. So, how many of you know what is Dirichlet boundary condition and what is Neumann boundary condition? Do you know this? No. Okay. So, Dirichlet boundary condition means you provide the value in the boundaries, and here you provide the derivatives. Okay, in Neumann condition. There is another mixed one side Dirichlet, one side Neumann, that's called Robin's boundary condition. There are many other types of boundary conditions. Like whatever information you have, you put that as your boundary condition. What? No, these are the information known. That's why I can apply the, these are standard numerical analysis techniques. So you apply the boundary condition, Dirichlet one side, Neumann another side. Huh? Least action principle, you say Goldstein. No. Least. Okay. Don't say that you won't do anything. So that is not least action. You have to do something. Least action principle doesn't teach you that you should be idle. Don't do it. So to follow the dynamics, so you can see we are gradually preparing ourselves to generate the descriptors for understanding quantum chaos. First is Shannon entropy, density correlation, macroscopic kinetic energy, rho versus minus chi plots. So Manoj, I was talking about this book, Cambridge University Press, 1993. Okay. So quantum theory of motion, de Broglie-Bohm representation. Now I am entering into another new theory, which you haven't seen before, at least. So quantum fluid dynamics, I told Madelung stuff. Now I am bringing in this de Broglie-Bohm representation. Here you can see this is a kind of Bible in quantum theory of motion. This is called quantum theory of motion. So motion of a particle experiencing forces originating from both classical and quantum potentials, that I have already shown what is a quantum potential. Now Newton's equation of motion, I can write it like this. That also we have seen. Okay. Now comes the question. Basic postulates of quantum theory of motion. Okay. And this is the picture. You know, in Copenhagen interpretation, you have wave or particle picture. Like if you do some experiment, you see either the wave characteristics or the particle characteristics. Now de Broglie started telling, and later on the total physics was developed by David Bohm. In fact, Madelung started that, then Bohm. And you can see there, this is called a Bohmian group. Okay. All throughout the world, there are some people, it's like a sect, you know. So I belong to the Bohmian group. So there are people from USA, Europe, Korea, many other, Israel, so Germany, Detlef Dur is there. So Bohmian mechanics tells you that, and that brings you like substratum quantum mechanics, where you won't have to bother about this. You tell that whatever you are seeing can be obtained if you bring in the wave and the particle picture together. So how it is developed, quantum theory of motion, how it is developed. So an individual physical system comprises a wave propagating in space and time together with a point particle which moves continuously under the guidance of the wave. So you can see the basic difference is we are bringing in both the wave and the particle simultaneously. The wave is mathematically described by the by psi at t, a solution to TDSE. Step by step, I have written only the gist. Okay, this is a maybe 1000-page book. You see the Pierre Holland's book there, Cambridge University Press. I had written the reference. So the wave is mathematically described by the wave function, time-dependent wave function. The particle motion is obtained as the solution RT to the equation V is R dot 1 by m grad S RT R equal to RT. So you can see simultaneously I know how the wave is defined and simultaneously I know how the particle is defined and how the motion of the particle can be governed. To solve this equation, we have to specify the initial condition. Let's say R0 at time 0 as R0. This specification constitutes the only extra information introduced by the theory that is not contained in psi RT. So we are not getting any extra information other than whatever is coming in quantum mechanics from psi RT. Only thing, the particle position I have to tell where it is to start with. An ensemble of possible motions associated with the same wave is generated by varying R0. Choice of R0 is arbitrary except that it cannot lie in a nodal region, since at these points grad S0 is undefined. And the probability that a particle in the ensemble lies between R and R plus dr at time t is given by rho RT dr, where rho RT is psi mod square. You can see a clear cut, say, theory which tells you how we define the particle and how you define the wave and how they are connected, their motion. Okay. So the probability of getting the particle is given by the corresponding probability coming from the time dependent wave function. And there is no particle in true sense. So these particles, they will constitute the actual motion so that you can understand what is happening in a dynamical setup, which cannot be obtained from the wave function alone. That's why you have to bring in uncertainty, this, that, etc. So which one? No, psi RT is psi RT, it is not ensemble. And that psi RT gives you a probability distribution. Right. And this probability distribution will tell you the distribution of the particles. Which? R equal to R naught, that is arbitrary. You take anywhere to so many answers. In Schrodinger theory, there is no particle. You won't have to bring in any particle. Yes. Yes. So now you see, we are, one thing remember, we talked about quantum fluid dynamics of quantum Helmholtz oscillator. Now we are going to the quantum theory of motion of Helmholtz oscillator. So here again, this is the Helmholtz potential. I do a piecemeal Rashford type finite difference approximation, velocity equation solved by Runge-Kutta method, and these are the initial and boundary conditions. Here we define a distance function. Okay, this is the standard way of doing it. Distance function, if you have two nearby particles, how you define this? Quantum Lyapunov exponent in terms of distance, Kolmogorov-Sinai entropy, and de Broglie wavelength. These are like standard say diagnostics for classical chaos. We have just given the quantum version of those diagnostics. So here we'll talk about, say, some quantum enharmonic oscillators. Say, as you can see, these are the Hamiltonians. These are, here you have the field, here you don't have any field, but you have some enharmonicity over here. And we calculated phase space distance function, quantum Lyapunov exponent, Kolmogorov-Sinai entropy, and standard diagnostics, autocorrelation function, power spectrum, nearest neighbor spacing distribution, spectral rigidity, phase volume given by this. So we calculated several of them. So I will show you certain results now. Classical and quantum phase space trajectories for case A. A1 is this, A2, A3, omega, and for case B, A1, A2. So this is classical phase plots. These are quantum phase plots. So here you can see, if you see the motion of the classical oscillator, it is like almost harmonic type oscillator, Px versus x plot. If you plot for harmonic oscillator, you get this type of behavior. Actually, in this, you can see two different sets of initial conditions. In one case, it is giving what is called a toroidal motion. That means the motion of the particle of this oscillator is only on a torus. You know what is called a torus? What? Okay. So great example is your Medu Vada, what you are taking. That's the best possible example. So how you get it? Say like bicycle tube. You cut it, you get one rubber band, that's one circle. Multiply by another circle. Whatever is formed is a torus. Okay, simplest possible way of telling. A circle into a circle. Now in this case, if the motion is on the torus, that is what we call regular motion. But if it like gulps the whole of this phase space, then you see the picture is like this. So for the same oscillator, two different sets of parameters, this is in a parameter space, remember. In one case you get a completely regular motion, in another case you get the say chaotic behavior. And I have told you what is the quantum version, how you get it. Remember, I have like we have generated our own diagnostics. In addition, what we are doing now, quantum equivalent of the standard diagnostics in classical chaos. So in this case, what is happening? The corresponding quantum phase plot, and how do you generate that I have already explained. You can see the behavior, and you see the behavior over there. So what we have shown that this is a torus, but having holes in it. And the holes are like Cantor set. It's a fractal. So we named that as Cantorus. You won't believe. Now the physics people, they are using this word Cantorus. It is a torus where each point basically they are giving you a Cantor set. Do you know what is called Cantor set? You don't know Cantor set. So you take, let's say, a straight line, divide into three parts, take out the middle part. Now you have the two parts, again you take out the middle part, take out the middle part. Do it ad infinitum. Whatever would be left to you is called a Cantor set. Okay. And you can find out its dimension. It's a fractal, its fractal dimension you can calculate very easily. Then you can see the Kolmogorov-Sinai Lyapunov entropies. There is no increase from t equal to 0 for classical and quantum. But there is sudden jump over here, which is typical characteristic of chaos, that Kolmogorov-Sinai-Lyapunov entropy will increase abruptly for the chaotic system. You can see the quantum system basically mimics. And if you think about the classical problem, also we have solved, although it is known, solved by many people, we have also solved, and I told you the Runge-Kutta, other methods, and this one is alternating direction implicit method for the quantum system. Phase space volume or uncertainty product. So this uncertainty product is almost no variation for the regular case, too much of variation over here. So we have talked about two different types of system, two different types of sets of parameters, regular and chaotic. Then we have talked about the power spectrum. Here you can see the power spectrum, and this type of power spectrum you get here, and another is just lying somewhere over here. This is the nearest neighbor spacing distribution. Like if you think about the energy behavior, two nearby energy segments in classical and in quantum, the corresponding energy values. So they behave the nearest neighbor spacing distribution. Say in one case, here you can see it is given like this, a function of spacing between consecutive energy levels, and they are also getting reproduced. Similarly, we have talked about, so those 5, you remember, quantum enharmonic oscillators I had written, and we have shown that the behavior is consistent, like whatever you are getting in classical, the corresponding quantum behavior exactly mimics, but the form is different, like torus is becoming cantorus or something like that. The main problem is we are within the density based mechanics. We talked about quantum fluid dynamics, we talked about quantum theory of motion. In both the cases, we are doing it in such a way that where we can get pictures like this. Okay. So these are different types of oscillators, and here you can see that whether it is the Wigner distribution or the Poisson distribution, that will tell you whether it is regular or chaotic, and that type of distribution, what you get in classical, the corresponding quantum version also, you are getting exactly the similar behavior. That means that if you take your oscillator to the quantum domain, in general, you can show that it will somehow translate its behavior from classical domain to the quantum domain. And this is, in fact, many people had objection like to our papers, and again, Michael Berry, another person who is Michael Berry from Oxford. So he used to come to IIT Kharagpur very often. So Michael Berry told me, he is expired now, that Pratim, don't tell this word quantum chaos. I told you, yes, I agree. Chaos is non-linear, typically non-linear, non-integrable problem. But by nature, quantum mechanics is a linear mechanics. So getting a non-linear behavior from a linear system, people are not very comfortable. So he coined a term, quantum chaology. So this is what is quantum chaology, what tells the quantum domain behavior of a classically chaotic system. Okay. So we did it for many other different types of oscillators and many other types of systems also. So, and they all mimic the expected properties. So I think just some interesting stuff. Here the confinement affected assisted bonding. So this is also we have done with dynamics that and we did real-time dynamics, we did ab initio AMD simulation. So what we could show that in fact like two neon atoms within this B12 N12 cage due to confinement they in fact form neon bonds. Okay, and this paper originally, in fact, in JCP, we had sent the paper, and the title we wrote, Can Confinement Force Two Unwilling Partners to Marry? That was our, say, title, because we are bringing two noble gas atoms and they are forming bonds. Okay. So in this case, they wrote that the editor wrote that your paper is accepted from the editor's desk itself. You simply change the title. So we had written this as the title: confinement-induced binding of noble gas atoms. So these are various. Now this is the BUMD simulation.
Essentially using some external field, and that is helping.
There, it's a very long story. Confinement, you see, this accelerates 1000 or 2000 times any given chemical reaction. We have studied Diels-Alder and other types of reaction in a confinement vessel. And there are certain reactions which do not take place at all in unconfined conditions. You put it in a confined environment. So now we talk about this as, say, catalyst-free catalytic processes. Huh? No, frustrated Lewis pair, yes, that is one type, but we did many B12 and 12, yes. So that we did several work on frustrated Lewis pair also. So, so these are various stuff, and also we had shown that the motion of that so-called dynamic system, this in another paper, we had shown that you can in principle follow the precisional motion of that say Ne2 dimer or He2 dimer, and that tells you that that is behaving, moving like a single entity, like a diatomic molecule. Okay, so that also we did some simulation to show that in principle you can find out the precisional motion of that diatomic molecule within that confinement case. But you take out the confinement stuff, immediately that will break down. I think there are many other things, but the time is limited. So we did in C60 cage. So these are the precisional motions. This is a classical Schrodinger equation that I don't know. These are the various quantities calculated over here. I think I should stop at this point. And if you have any question, I have, you see that I travel from one place to the other, etc. You have learned reactivity dynamics, you have learned quantum chaos, and obviously the starting point of quantum fluid dynamics, quantum fluid density functional theory, and quantum theory of motion. So these are all density based dynamical theories or time dependent theories, which may be somewhat different from what you have been hearing in other lectures.
Thank you, Professor Chattaraj, for introducing us to so many topics that we didn't know before. So the floor is now open for questions.
Thank you.
So I'm just wondering about the, so we have a lot of density functionals implemented in quantum chemistry software, but not much on the current density functional or
There
things
is
which
a
are.
current density functional theory. This is a standard developed theory. It's called current density functional theory. You give search in Google.
No, I'm talking about practical implementations of those.
No. Actually, there are several groups. They have borrowed our say which we developed our in-house, but we are bringing in explicitly current density. So, but it is required if you want to solve any time-dependent problem. Exactly, current density you cannot bypass. I'm telling you, because the Runge-Krauss proof also says that time-dependent. If you want to see, they are not density functional. They are density and current density bifunctional.
One other question is about when you had the generalized nonlinear Schrodinger equation, how do you solve it numerically?
How do I solve numerically? We have about, I think, 27 pages physical review A paper. In one appendix, maybe 5-6 pages we have derived. This is alternating direction implicit method, the way we have done the split operator technique.
And you always get a unique solution, or there are issues with the solutions there?
There are hell of a lot of problems. It took 2 years for me to set the program. This, I told you about 70,000 statement programs. Okay. And you are dealing with even helium atom. You have 6 space variables. You have 1 time variable. Okay. How many, say, and when you have a cylindrical problem, you have Rotilde axis, you have phi axis. In order to converge, how many mesh points will you take? You see the dimension of the arrays. Think about that. Even if you write 10 by 10 by 10, that itself is 1000. Okay. And when I was doing it, there was hardly any computational facility, I'm telling you. It's very, very difficult. 2 years, I'm telling you, it took. And that time we used to go with those gunny bags full of decks. So you have the cards, computer cards. So that may be, you will tell, prehistoric.
So about that confinement, so what makes that confinement to make like noble gas to react? Like, what you are thinking? Like,
yes, a confinement is a big story. I cannot tell you it in 2 minutes.
means like
Actually,
what is the impact and
confinement
factor?
does many different things. Okay. So particularly the acceleration of the chemical reactions. You know, as I told you, 3 orders of magnitude enhancement in the rate of a chemical reaction. In some cases, the chemical reaction, and these are experimental stuff. And he was talking about frustrated Lewis pair. There is, say, Keeker-Butyryl CBN. Then you have EX box 4+. So there are many such cavitants. In fact, people are talking about getting 3 persons getting Nobel Prize in MOP, POP, etc. So wherever in the cavitant you put the chemistry, physics, stoichiometry, everything will get changed. Okay. So,
what are you thinking? Like the impact and
so
factor?
suppose if I put some 10 kilo weight at your head and ask you to run, you won't be able to do it. Okay, it is like this.
Thank.
And sometimes perhaps you will be more energetic and to run much faster.
So when you talk about excited state density, how it is different from ground state density? Like, what's the difference between excited and ground state density? Because in wave function method, we can take linear combination of ground state and excited state wave function, and we can follow the coefficients as population.
I'm not getting your question.
Like,
can you explain it a little bit?
In a wave function method, we can take a linear combination of ground state wave function and excited state wave function. And when doing quantum dynamics, outer population changes, we can follow by following the outer coefficients changes with time. So when you tell about excited state density dynamics, how the system is defined in terms of excited state density. Do you take linear combination of density, or what exactly is that excited density? How it is different from ground state density?
You start with the excited state wave function. You
Oh,
have the
it's, so-
definition of the density. You put your excited state wave function in the definition in integral psi star psi d, say dr2 to drn. That will give you the density, excited state density. What is the problem? I am starting with excited state wave function. You everywhere, huh? Huh. Which one? No, no. But what do you mean by let's say electronic excitation? Can you tell me what is electronic excitation? No. That is you are telling the same thing in a different language. What exactly physically does it mean? Which wave function will explain that? There is something called excited state wave function, isn't it? If you solve the Schrodinger equation HI equal to HI, in principle, you will get all the wave functions. Do you know this? So why are you in this workshop? Go out.
Sir, is it
We are doing everything in 3-dimensional space, remember. If you go to the wave function even for helium, it's 6-dimensional space. Okay. No. You take the mic.
we calculate the reactivity parameters for the ground state?
No, the others also should be here. No.
Is
You
it
see, the
possible?
questions are never wrong. Only the answers can be wrong. Okay. No, actually, you see, when you talk about electron affinity and ionization potential, that concept, the way we are defining it, it is essentially for the ground state energy distribution. Okay. And there, if you are adding an electron, if you are taking out an electron, and how much energy is released or how much energy, say, you will have to supply, that will give you ionization potential or electron affinity. Now, when you say that it is already in its excited state, there are two different stuff. One is ionization, another is excitation. So, if you can tackle both of them properly, there is actually no problem. But you must differentiate between two different electronic processes, electronic excitation and ionization.
Check.
This is so when you talk about I and A, you are talking about n+1, n-1, there's an ionization problem. And when you are exciting it to some excited electron, say this excitation problem. Okay. So they are two separate problems.
Which is not easy to calculate actually.
No, but what will happen, say if you want to take the electron out, let's say, before excitation and after excitation, they are totally different because the orbitals of whatever picture you take, there would be relaxation and other effects. So one above and one below, they will not commute. These two operations will not commute.